our first expert is Dr. Naveen Kumar ji, who will deliver his lecture on energy efficiency and energy auditing in cogeneration plants. So, first of all, I will introduce today's first session expert, Dr. Naveen Kumar ji. Dr. Naveen Kumar ji, an assistant manager in Grasim Industries Limited, Aditya Birla Group, Andhra Pradesh. He completed his MTech in mechanical engineering from JNTU, Kakinada in 2011 and his PhD from BIT Bangalore in 2023. Dr. Naveen Kumar has energy manager certification from Bureau of Energy Efficiency, Ministry of Power, Government of India, which he earned in 2016. He also holds boiler operation engineer certification from the Boiler Board, which he obtained in 2014. With 16 years of experience, he has worked with different type of boilers and he has been involved in energy management studies. Currently, he works in operations and maintenance of utilities as well as training and ISO documentation preparation. We are excited to hear from him today. Please join us in welcoming Dr. Naveen Kumarji for his session. Welcome you, sir.
Yeah, thank you. This is Dr. Naveen Kumar. As Sar said, have 16 years experience in different type of boilers and different energy management studies also. Given so many studies, and our target is to reduce the generation cost. As you know, today's market we are getting from IEX due to the renewable sources. We are getting power at 5 rupees. Sometimes it came down to 4 rupees. But due to the thermal power with the low capacities, we are getting more than 8 rupees. So we are focusing on those parameters. Now we are getting 6 rupee, less than 6 rupee from supercritical boilers. But existing boiler getting it is very difficult. So we are doing so many studies. So coming slides, I will explain briefly. So shall I start the session?
Yes, sir. Please start, sir.
Yeah, this is current at 31st March 2024 scenario. Our 75% generation contribute from the coal-based plants, coal-based thermal power plants. Remaining their remaining contribution very small amount only. But non-conventional source of energy dependency is very difficult. Why? Because we have a grid frequency. Now India we are getting 50 hertz frequency. As you already knows, so many incident has happened due to that. Last 2 years back, I think so. North side, due to this grid disturbance, the total power disturbance has happened for 2 hours, and so many trains and airport authorities are totally were blocked due to this grid frequency. So we are not that way. We are at least maintain some plans for maintaining of the grid frequency. Renewable energy source is good, but we can't depend on the renewable source 100% due to the unavailability of the power at continuous power. So this is the energy generation scenario. Coal contributing 75%. Uh, Remaining things as the solar 6%. Now solar is going to increase biopower 0.89%. Now government has concentration on biopower also. Nuclear also they are developing 2.77%. So this is the total installed capacity by March 2024, 30%. Coal installed capacity is around 50%, solar 18%, so on. So this is the brief scenario of the power in India market. So coming to installed capacity of the thermal power plant. This I get from IEX person and some internet source also I have taken this data. So Indian total installed capacity in India is 442 gigawatt. Out of this, state sector contributing 106.332 gigawatt, whereas the central means from NTPCs, National Thermal Power Corporation. They are supplying 102.274 gigawatt, whereas in private sector contributing more than those two. So 219.691 gigawatts. So this is the installed capacity in India. And coming to contribution of the sectors, thermal sector is contributing 1324.11 billion units, whereas in hydro and nuclear it comes under very low. So this is my main contents which I'm going to present. So I'm starting with the Rankine cycle with reheating and regenerating concepts. Then power plant. What are the then I could explain the main cycles of the power plant. Why? Because for each and every equipment we should concentration to reduce the power consumption. So according to that, parallelly we could go for that go for the viability of the plant. So components of power plants, detailed explanation of the each and every plant, every component. So after that, I'll show you the one practical energy audit study that was conducted in 150 megawatt. So that I'll show you here, and performance improvement measures from that energy audit study. What they have given the measures and what is the payback period after taking those measures. So these are the points I should cover in my session. So lastly, recommendations, what they have given. They have given three type of recommendations. One is short term, long, medium term, and long term. I could show you detail. So as you know, this is our basic Rankine cycle. Uh, our plants, thermal power plants, and steam heat engines, steam turbines are reciprocating here, working on those cycles. Here, mechanical work. Wow, we are getting mechanical work from turbine that will couple to the generator to get the electricity. So this is the basic funda. Next, Rankine cycle. The heat energy supplied through boiler. That means we are supplying input to the fuel and air that converted into the steam. That high pressure steam we will supply to the turbine for rotating. According to that, generator and alternative is going to rotate. After passing through the steam turbine having different stages. Now we have a three type of turbines, each having different stages. We have a HP turbine. HP turbine having 9 stages. LP turbine 9 stages. IP turbine, sorry. IP turbine having 9 stages, and finally LP turbine having 10 stages. Total we have 28 stages. I could furtherly I could show you how the stages are work and what the bleed we should take to get the regeneration. After passing the stages, fluid is allowed to condense back into the water stage. So after passing through the stages, the steam getting, we can't say steam, it is a dry saturated, so wet steam. So by condenser going through the condenser, it will get to the water. Again, we should send to the boiler for heating purpose. So here there is so many friction losses because total system comes under the pipings only. So as compared to the thermodynamic losses, these losses are very negligible and it will very complex. Suppose if you take to consideration, so friction loss could be neglected in any power plant, not only India and foreign also. So these are the process, as you know, isentropic compression from 1 to 2. The pump work depends on the isentropic compression. The pump take the low pressure water to the high pressure by using of external energy source that is nothing but electrical energy. Process 2 to 3 constant heat addition in the boiler. So the heat supplied to through the fuel and air or supplied to the water that will convert it into high pressure steam and high temperature steam also. The steam as you know we have a three type of steam: wet, dry, and superheated steam. But power plant, we are using superheated steam only. Why we are using that will explain in later slides. Next, 3 to 4 is the isentropic expansion, which is going to take place in the turbine for getting the power. And 4-1 is the heat rejection in the condenser. This condenser water is directly connected to the cooling tower. As while explaining this section, I could explain both the performance. Okay, this is the equations as we know, m into h3 minus h2. So this is the pump work. As a pump work, we are going to neglect because it is very less work compared to the turbine. So we could concentration on the boiler and turbine part. Work of turbine minus work of pump by heat supply in the boiler. So we are going to eliminate this pump work. Finally, we are getting mass into h3 minus h4. Mass is nothing but steam. Here by m into h3 minus h2, this mass is the fuel mass. Okay, next. Random cycle with reheating concept. We have two concepts. One is reheating and another one is regeneration. While you just see this figure, while expanding the steam after going to the turbine H3, this was not supposed to here. Actually, turbine is in reverse stage. Okay, we are supplying steam to the first stage of HP turbine. At the end of the HP turbine, that means ninth stage. This is going to the boiler again. Why it is? Suppose say if you the output of HP turbine, if you use in IP turbine, already there is a loss of the heat and temperature. Generally, this condition is 35 kg, 37 kg, and 333 degrees centigrade. As per our practical experience, I'm telling you. If you suppose to supply this steam to the IP turbine, there is a chance of condensation. So there is an enormous release of the condensation, and moreover the fumes, and there is going to damage the turbine blades. So there is a enormous drainage fraction, moisture content is there. So for that purpose, this reheating concept has been introduced. The line which is going from the turbine to the boiler, it is nothing but CRH, cold reheat steam. As per our power plant terminology, we can say that is the cold reheat steam. This condition is 37 kg and 337 degrees temperature. While going through the boiler, there is a reheater arrangement in the boiler. While going to the boiler, I could explain this clearly. What's the reheating and all the things. It could be heated, and again the output of the reheater is coming to the IP turbine. This is nothing but HRH, hot reheat steam, as per our power plant terminology. Hot reheat steam. This condition is the pressure is same more or less, but the temperature is developed 540 degrees, as we have given here 540. So that temperature is going to the IP turbine. Here, due to the space constant, I have not shown the LP turbine. The IP turbine having the again 9 stages, and after that it is going to the LP turbine, which is having the lot of blades. So the LP turbine last stage having there is a fencing arrangement. So at any cost, we are getting the wet steam at the LP turbine. So there is a special arrangement. So I could explain while going to the turbine section. So I have explained. Reheat temperature is close to the HP turbine inlet. Pressure is 1/4. That means we are giving here 140 kg pressure at 150 megawatt. We are getting 37 kg at the HP turbine outlet. Again, it will go to the IP turbine for 37 kg and 540 degrees temperature. So this is the regeneration concept. There is a second concept is regeneration. So at the end of turbine, we are getting 50 degrees temperature. But while going to the boiler, there is a number of stages of the turbine. Suppose HP that much of high pressure we are supplying to the turbine blades, there is a chance of steam leakages. So we have at any stage, at any cost, we have a sealing arrangement for HP, IP, and LP turbine. Those sealing we are supplying to labyrinth gland. That gland is nothing but labyrinth gland. As per power plant terminology in anywhere, if you see the three type of turbines, you could see the labyrinth glands. So we are supplying the steam to the labyrinth glands for avoidance the leakage. But we are supplying here 140 kg pressure. What is the atmospheric pressure? 1 kg. So for that purpose, there is a chance for escaping the steam from the turbine tip to the casing. So we have a so for that purpose, we are taking the steam as a bleed steam and we are supplying to the heaters. There is a two type of heaters here, HP heaters and LP heaters. Turbine first stage we are giving to the LP heaters only. After there is a derator arrangement for deration of the water that I will explain later slides. After derator, there is a feed pump. That feed pump arrangement is there. That feed pump again supply to the water to the boiler through HP heater. So that case, there is a two streams here. One is condensation stream and another one is a feed water stream. Condensation stream we are using LP heaters, whereas feed water stream we are using HP heaters. And then that LP heater is act as a heat exchanger only. We have studied parallel flow, counter flow, and cross flow, right? As it is act as a heat exchanger. This is in our power plants. All heaters are the counter flow type of heat exchangers. So it temperature, the limit of the temperature is increase of the temperature is 10 to 20 degrees. So we have a four type of LP heaters. One is LP heater one, that is immediately at the condensation stage. Later on, there is a three LP heaters in between CEP. There is a pump arrangement after heaters. That is nothing but condensation extension mode. That will I will show you. The one practical sketch is there. I'll practical screenshot is there. I'll show you by that time. So this is the schematic diagram of thermal power plant. So coal storage is there. Bulk of the coal coming from the outside and it come to the coal handling plant. After crushing and all the things, it is going to the boiler. So there is a air arrangement also there with from fans, FD fan, PA fan. We are supplying air to the boiler. So there is these are the all main circuits. Just see once coal handling plant. These consist of the total belt conveyor, crusher, vibrating screen, bunkers. Whereas in ash handling plant, ash handling plant for the output. That means the burning after burning of the coal, it is going through the chimney. In between chimney, we have a disarrangement. Why we have the disarrangement? There is a limitations from our factory department, not only Andhra, in every state. It is SOX, NOx, and SPM. SPM should be maintained less than 50 ppm. Earlier it is 50 ppm. Now, as per the Factory Act, that was comes under the to 30 ppm only. And SOX, NOx comes under, earlier it is NOx is 600 milligram per centimeter. Now it will come down to 300. Both SOX and NOx only 300 only. So this is the ash handling plant. Coming to the next one, water treatment. The water treatment is the most important part, which boiler life depends. If water treatment is not there, the boiler life is going to down because due to the rust and all the things. There is a AE system already I have explained, ID fan, PA and SA fans. Sometimes some places it is in SA fans, sometimes it is in FD fans, but both they are giving the same purpose. Then the next cycle is reheating cycle. As I have explained in earlier slide, there is a CRH and HRH arrangement, cold reheat and hot reheat. There is a next cycle is there is a regeneration system, HP heaters, LP and derator. So this is the practical screenshot. This is the boiler. This is the coal handling, coal feeders. The coal which is coming from the coal bunker after crushing from the crusher, it is come down to here. So these are the fans. There is a two SA fans and two PA fans. ID fan for extracting the flue gas. So these are the supplying air to the boiler through APH, air preheat heat exchangers. So just see the temperatures. What is the temperature here? 44 degrees and 1544 mm of water column with that heat, that much of temperature, and this pressure they are going to supply. After getting the air preheater, after exchange takes place from flue gas to the air, the air is heated up at 218, and this some minor pressure loss is there due to the tubes arrangements. It is going to the wind box. These were the wind box for supplying air, air at the bottom. And this is a SA fan arrangement. These for the territory combustion. Suppose say if you consider this PA fan, there is a combustion happening at this place. There is a chance for escaping the finer particles. If the finer particle is going to escape, our coal is going to wasted 40% at outside, and the LY, loss of ignition, also is going to increase. For that purpose, there is a arrangement for that term is nothing but territory combustion. So we are supplying air at this place. There is a complete combustion happened. This is the concept of CFBC. Actually, we have a different technology arrangements. So combustion point of view for medium capacity, CFBC is the best option. This will give combustion efficiency 99, more than 99%. Okay. Next, this is the already while coming to the each and every part I'll explain. Just have a look. This is the bed ash polar arrangement. That means drained ash is going through the bed ash polar to the atmosphere. So, hello, there is a J-seal fan arrangement for supplying the air at this cyclone. Cyclone concept, you know, as outlet of the furnace having the minor particle with flue gas. If you leave the particles, that particle having the content of the energy, that means heat value. So if we leave those particle to the atmosphere, there is a loss for chance of the ignition. So for that purpose, there is a cyclone concept. While rotating this one, it will come again fall down to the, this is nothing but cyclone loop seal termed as. So while supplying the fan, it is again fluidization happened. Here there is a one fluidization. Here there is another fluidization. After fluidization, that will come down to the furnace for maintaining of the bed. So this is the, after that it is going to the superheater, reheater, economizer, APH, finally ESP, and go to the atmosphere through ID fan. So this is the coal generation plant. We have a here arrangement also. As we explained, there is a number of bleed steam arrangement at the turbine that will supply to the heater, and there is another bleed also is going to the process. Here we have a chemical plant. We need the steam for heating purpose. So we are supplying. We are taking heat from the from our plant. It is 15 kg and around 16 to 17 tons. While it is going to that, it is the one purpose is heating for the process. Why it is called cooling? We have a chiller arrangement. You know the VAM, vapor absorption machine. Vapor absorption machine is working for giving the coolingness to the plant. So it is a, for big capacity, the plant people are using VAM only. For small capacity, we are using VCM, vapor compression refrigeration, as our ACs are domestic ACs are working. So this is the cooling arrangement. We are supplying one line to the VAM. That is nothing but 4 kg and 2 tons. There is a special arrangement, nothing but PRDS, pressure reducing desoperheating station. Through that, we are supplying to the VAM chiller for getting the cooling. So already I have explained this heating, and there is a generation given to the grid. So this is the coal handling plant. There is a hopper arrangement. Again, after that, there is a screen. This is nothing but a belt conveyors. Belt conveyors plays a vital role in thermal in coal handling plant for transport the coal from one place to the another place. If it is a sea coast area, there is a large size of belt conveyors arrangement you can see. As per the applications, the belt conveyors numbers and size they are using. Now this is the crusher house as I have explained. So there is a crusher arrangement and after that there is a screen arrangement. So this is the vibrating screen. So the purpose of vibrating screen is to remove the oversize undersize coal, because in CFBC we need the 6 coal size. If more than coal size going to the boiler, what happened? There is a chance for increase the retention time and that will convert it into the LOE, loss of ignition. So loss of ignition, nothing but we are going to waste the coal. So for that purpose, this is the vibrating scene application. Then it is going to the trolley crusher. After that crusher, it is going to the trolley and fill the bunkers. So this is the ash handling plant I have explained. As bottom ash, this bottom ash come from the furnace. As per the bed convenient, we are getting this bed ash and then go to the economizer hopper. There is the economizer arrangement is there. There is a hopper arrangement, because each and every place we have a hopper arrangement for remove the ash. Otherwise, as I have explained, there is a pollution norms that the pollution control board person from government is come and give the notice simply if you are not maintaining like this. So this is the ESP, electrostatic precipitator, which works on the um, positive and negative ions concept. There is a two type of arrangements. One is collecting electrode and another one is emitting electrode. Collecting electrode means for collect the dust particles, and emitting electrode it strike the plates and it will collect in the these hoppers. Based on the capacity of the plant, this hopper arrangement and number of hoppers is there. Finally, the gas going to the atmosphere through the chimney. At the end, this temperature, the gas temperature is little most 120 130. As per the, there is a one concept for the coal, that is a sulfur dew point temperature. So we could reduce the flue gas temperature not for the beyond the sulfur dew point temperature. Why? Because if you reduce the temperature less than that dew point temperature, it will chance to erode the duct arrangement and ID fan impeller also going to collapse. So for that purpose, every OEM will supply, while erecting the boiler and commissioning the boiler, they could supply what is the sulfur dew point temperature. Okay, next. So this is the first cycle, first stream, fuel and combustion. Here there is a, as I explained, chemical energy is directly converted into the combustion. There is a while combustion takes place, heat release from the fuel, and that fuel, that heat is going to use to convert water into steam. There is a different type of fuel arrangements. The fossil fuel, coal, oil, and natural gas. Byproduct fuel. This is coke oven gas, blast furnace gas. These are the gas come from the steel plant only, not in everywhere. Chemical fuel, hydrogen, ammonia, hydrogen boilers also there we have. Next, nuclear fuel, Ukraine and plutonium. So these are the total fuels. Then further the fuel is divided into both primary and secondary. Primary fuel for coal, wood, petroleum, and natural gas. Secondary fuel, after treating this fuel, it converted into coke, flue gas, petrol, diesel. So this is the property of coal. Coal, we have a four type of coals. Mainly three types, but wood also we are considering as a fuel. So lignite, bituminous, and anthracite. Lignite is the youngest one, whereas this is the second stage of coal. Anthracite is the last stage of coal. This is the oldest coal. Now we are not getting the anthracite coal in India. We are getting bituminous coal. That range is 2,400 to 4,200. Now we have designed, this was mentioned by the OEM while supplying the boiler to us, as our GCV is 4,050 kilocalorie per kg. So again, this coal is going through the analysis. There is a two type of analysis we have: proximate analysis and ultimate analysis. These are the proximate analysis for the initial analysis. It's all fixed carbon, volatile matter, and moisture and ash is coming from this. There is another analysis that is nothing but the ultimate analysis. So In ultimate analysis, each and every element is coming from the picture that oxygen is directly contributing to combustion that I explained later coming slides. So this is the proximate analysis of coal. It indicates percentage of fixed carbon. Ultimate analysis, there is a carbon that is nothing but carbon. That is the exact value. This is the fixed carbon having the all elements, volatile matter, moisture, ash and moisture in coal. The amount of fixed carbon, the here moisture and ash is something we are getting lost from these two parameters. Whereas in carbon and volatile, actually carbon meant for the burning purpose and volatile it gives the ignition of the coal. Actually, while startup, we are giving initial inching. There is nothing but initial inching. Generally, we have started boiler from the diesel only. After certain temperature getting, that means nothing but more than 380, 400, more than 400, we are giving initial heating. So, due to the volatile matter, it gets the catch the fire, the coal. That time we are not supposed to give the continuous supply to the boiler, the coal, due to the there is a chance for dumping of the coal. That will directly converted into the CO formation. So we should take care while light up the boiler, while seeing the O2 percentage, we are giving supplying the coal here. So this is the approximate analysis table, detailed approximate analysis. Here we are getting the Indonesia coal also. We are using Indonesia coal here. There is a South African coal and Australian coal. These are the values. Just see. So this is the ultimate analysis. As I have explained, from ultimate analysis, we are getting hydrogen, nitrogen, oxygen, sulfur. Each and every parameter we are getting, but it will take time. For preliminary analysis, approximate analysis is sufficient for calculation of the direct efficiency. But for in detail, we are going for the losses method. That means indirect efficiency. That method also I will explain later. There is a determination of air quantity arrangement for combustion and volume of the gas also. So I have compared in our practical industry coal size, coal analysis. Yes, we are using India coal and Indonesia. These are the brief analysis from the ultimate analysis. So the main point of in coal handling plant is storage. How to store the coal and how to utilize the coal. So there is so many losses associated with the coal handling plant. Those are the oxidation losses. Oxidation loss is nothing but while coming to the oxygen coal from the supplier, there is some percentage of moisture content. We are not using directly the coming coal. We have kept it some place for some period of time. After that, we will use the coal. You just if we check the coal in that moisture percent, it will come down to 10 to 12%. So there is a loss for due to the oxidation. So we have considered 1% of the oxidation from the coal that time. And there is a windage losses as you know, coal will dump in atmosphere only. Fines will go through the winds. So we have considered here 0.5 to 1%. There is a coal size. Coal size is there as I already have explained. 6 mm. 6 mm coal size for the CFBC boiler and AFBC. That terminology I will explain while coming to the boiler point of view. This is a blending of coal. Why blending of coal? There is a two factors. One is financial factor. Suppose if we use Indonesian coal is little more costly than the our India coal, but GCV is more than the India coal. So for reducing the finance point of view, and there is a chance for increasing the LOE if you use the pure Indonesian coal. Yes, I'm sorry. Hello, hello. So
Sir,
coal.
yeah,
Yeah,
please proceed, sir. I
yeah.
think there is
Somebody has asked something. Yes.
no,
Okay.
sir.
Okay. So coal blending important for the for financial point of view and usage point of view. So this is the coal conversion. This is the most important thing which plays a vital role. As I told you that there is a as received basis, a dry base and dry basis. Dry base for the this is special purpose only, but we have used here is ARB and ADB. If you see, if you done the analysis on ARB, it will convert it to ADB. If you done the ADB, we will convert it to the ARB due to this formula. So second one is feed water chemistry. As I explained, feed water chemistry is the most important factor as the boiler life is going to depend. Why? Because if it is not good, we'll get the corroded and live damage the tubes and damage the parts. Whatever it is, the happened is happen. So this is the feed water chemistry. So depend on the source of water. We have a here, we have a R1DM. RO, as you know the Dubai technology, we are taking water from the sea source, sea water. After that, it will go through the RO system. So it will remove the impurities. There is so much of stages are there, but just for sake of your convenience, I have explained rightly and due to the time constraint also. So before using this, impurity should be removed, and feed water impurities are responsible for the corrosion and scale formation in the tubes, as I explained. This affect and moreover, corrosion and scale formation, and also it will affect the heat transfer also. Suppose say if we are using 90 tons per hour for getting the 150 megawatt for that much of heat. Suppose say if any scale formation happen, what happen? We are supposed to give excess coal for getting the that much of heat. Why? Because if you are not giving that much of parameter as per design parameter, that turbine inlet valve won't open. There is a logic for the turbine inlet valve. Suppose if you bypass the valve, it will damage the turbine. So this is the most important thing. Boiler feed water salt, calcium, magnesium, as you know, the calcium and magnesium plays a vital role to respond the scale formation. We have to remove for that. And presence of silica also. Why silica? It would not insoluble in water. It will transfer to the steam and which deposit on the turbine blades. So due to the deposition of the turbine blade, there is an imbalance and there is a chance for increase the vibration and finally it damage the turbine. So these are there is a two type of treatments. One is internal and another one is external. Internal treatment, the soda ash and caustic soda. These for small boilers only. But big plants we are not using this because of there is a so much of deposition of the salts. So we are not using this. We are using the phosphate treatment, which is in HP dosing pump. This HP dosing pump supply water supply will give to the boiler drum. As already I have shown that boiler drum while in the screenshot. So this is supplied to the boiler drum for remove the this one. Just see, have a look for this. We are using trisodium phosphate Na3PO4 with water reaction. It is converted into Na2HPO4, sodium hydrogen phosphate. So this property having there is a one important property for this. It will bond the particles. So after bonding that particles, it will go, the density of the particle is going to increase. So it was come down to the drum, the bottom of the drum. That we will remove by blowdown system. I will explain while coming that picture. And NaOH, this is the caustic soda. This is responsible for increase of the pH. So it is useful for us. There is another one is there is an internal boiler treatment. So this is we are using hydrogen N2H4. So sodium salts also using, but it is not using nowadays because of the solids deposition more over there, and we are giving frequent blowdowns. Blowdown also there is a loss of the heat. So the as per OEM they are not supposed to give the blowdown at regular intervals. So N2H4 is directly react with oxygen. It converted into N2 and 2H2. So nitrogen gas will go through from the air vent, and this converted into water. As a deaerator is a part which takes place, which is most important in the boiler power sector. Not only power sector, process sector also. Why? Because here there is a two type of treatments: mechanical treatment and chemical treatment. Mechanical arrangement for there is a trace arrangement. We are supposed to give the steam here that will go into the upward. While coming to the feed water, it will get heated up, and there is a any gases that will remove through the air vent through steam. So this is the heating arrangement, and that is the mechanical deaeration. Chemical deaeration for the adding of the hydrogen. So this is the external water treatment. I'm not going through this one because of the time constraint. Just have a look. Two treatments are there. R1 DM treatment. There is this is the very last of the subject. So DM after RO process, we are getting feed water through the DM plant to the boiler. So this is the recommended water parameter. Here we are considering feed water. There is a feed water arrangement. We have a four type of steams: feed water, condensate, main steam, and drum. These are the parameter we should maintain. Otherwise, our steam quality is not that much of good for getting the power. So finally, the comes under the boiler part. This is the introduction of the boiler. It is a closed vessel, for converting the heat into energy. The generated steam transfer to the process heating, as I explained earlier slides, and power generation also. Why we are using the water? Why not using the other liquid? So this is the point. While you increase the heat, the steam volume it getting 1600 times than the other substance. So it already getting that much of volume and that much of pressure also. So this is the one of the terminology as per IBR norms. Is a closed vessel exceeding 25 liters of water capacity. Then only it is called a boiler with all mountings and accessories. Mounting is nothing but pressure gauge, temperature gauge, all water level indicator. These are the mountings. Accessories for operator, reheater, economizer. So this is the schematic diagram of the boiler. You just see that. Here primary arrangement already I have explained earlier slides. This is the drum arrangement, and this is the downcomer. 3 is the downcomer. Coming to the after downcomer, water going to the water wall. After getting the sufficient heat, it get converted to dense, and it will transfer to the different stages. There is a plate separator, high temperature separator, reheater, low temperature separator. There is a reheater and economizer arrangements. So these the main difference concept of the boiler. Main concept: fire tube boilers and water tube boiler. As you know, fire tube we are using fire and hot gas in the tube, and water remain outside the tube. These are the type of the boilers. While water tube boiler, water inside the tube and flue gas outside the tubes. These are the types of the fire tube boilers. These are the major difference of the fire tube and water tube. Up to 16 kg for cm square only we are using fire tube. For maximum up to how much pressure we are using water tube. All supercritical boilers and big plants are comes under the water tube boilers only. So these are the major difference. So selection of the boiler. How we can select the boiler? These are the thing: space availability, fuel and water availability, initial cost of the installation, operation maintenance, load dispatch center. Suppose it is a load dispatch center, SLDC is not nearby. We will again put the money for getting the more lines, more high transmission line from the department. So steam generation rate and working pressure. So there is I already explained there is a different technologies of the boiler. That is AFBC, CFBC, atmospheric fluidized bed combustion, pulverized fuel. These boilers are using nowadays, but AFBC for small capacity, fluidized bed combustion for the medium to somewhat is high capacity also. For PF, pulverized fuel for high capacity only. That means 660 and 800 megawatt. All NTPC they more than 600 megawatt comes under the PF, but less than the 600 megawatt comes under the fluidized bed boiler. but less than capacity also they are using PF, but it will not give that much of efficiency. So as already I have explained, this bed metal, there is a bed metal concept. The fuel would not directly combust in the boiler directly. There is a bed metal arrangement. That bed metal is going and striking the fuel while fuel is dropping into the boiler. After there is a sudden burning is not happened. There is a separate layer by layer burning is happened. So this is the maximum bed size, 0.5 to 3 mm. But mostly we are using 1 mm only. As per OEM, they have given 0.5 to 3. Boiler combust at 840 to 950. As I have, while showing that screenshot, I have shown this. This is the capacity of the boiler, and these are the fuels, coal, washery. These are all fuels we are using, and this is the advantage for it. Less emission, combat boiler driven, high boiler efficiency. Already high combustion efficiency, not boiler, sorry. Already I have explained this. So this is the supercritical concept. Supercritical at this point, that is 221 bar and 374 degrees centigrade. This is the supercritical point. After this point, the water directly comes converted into the steam that will be used into the turbine. Otherwise, in supercritical boiler there is a no drum. There is one small vessel is there for that vessel meant for the partial load bearing. While subcritical boiler all having the drum, because steam having some suspension, some time to segregate from the drum from the feed water. So that again that steam going to the different stages for getting the superheat. So these are already I have explained: CBD, IBD, PBD, and ABD. These are the terminologies. Continuous blowdown. Continuous blowdown. It is giving as per the parameters of the boiler. We are giving continuous blowdown. Intermediate blowdown. If any parameter deviation happen more than the design limit, we are giving this IBD, PBD. Emergent blowdown for if these three blowdowns are not working, we will give the emergency blowdown for saving of the unit. So this is the performance evaluation. We will evaluate the boiler through two ways. One is evaporation ratio and another one is efficiency ratio. So like so evaporation ratio means for the output by input. Output is the steam, mass of steam into enthalpy of steam, while input is mass of fuel into calorific value. So both that calorific value and enthalpy is same for steam. So mass of steam by mass of fuel give the exact evaporation ratio. That will that values I will show you. So these are the performance evaluation of the boiler, enthalpy gain. So already I have explained. This is the 4 to 5, 5.5. This is the evaporation ratio range. For different boilers, different evaporation ratio. So this is the boiler efficiency method. There is a two methods. One is direct method and indirect method. So this is the direct method. Direct method formula I am giving here. So mass of steam by mass of steam into enthalpy difference of steam and feed water by mass of fuel into GCB. Here we are not getting the exhaust efficiency and exhaust losses. There is a 9 type of loss we have. That loss I will explain in coming slides. Those loss will not come to this. These the we consider preliminary for this efficiency only, not for the detailed point of view. So the three T's, these three T's plays a vital role for the good combustion. If we are not getting the good combustion, we are not getting the good steam, and we are now the optimization of the fuel also we are not getting exactly. For that purpose, the three are more important: temperature, turbulence, and time sufficient. So too much of fuel, and too much of air also is very dangerous. That will convert it into unburned, and there is a chance for blasting of the boiler due to the CO formation. If you give more excess air, more oxygen, that so much of heat is going to transfer takes place and going to the atmosphere, that will be wastage for that is a fuel loss. So for ensure complete combustion, we have a excess air arrangement, and OEM also will give 50 excess air concept. For boilers, as per the capacity and size and as per the type of boiler, they are providing 15 to 30% excess air. On CFBC, we are getting 20 to 25%. Whereas while coming to the PF, polarized PF, it is coming 15 to 20% only. So these are the indirect heat loss method. There is a two here. So these loss, after getting the heat loss, while we subtract the from 100, we are getting the boiler efficiency. This is the ultimate analysis. Ultimate analysis for the all. This is a practical as per my company analysis. I am supplying to supposed to give here. So carbon, hydrogen, nitrogen, oxygen, sulfur, moisture, ash, GCV. This is the unburnt fly ash. I already I told you 0.11% bottom ash. So less fly ash 4.89, but little this is little most higher than the normal operation. Later on that we have reduced this also. So bottom ash LOE and fly ash LOE. So this is the theory. This is the calculation part. Theoretical air requirement formula. From here we are getting the how much theoretical air required. Already I have explained two type of airs. One is theoretical air and another one is excess air. So this is the excess air formula. This O2 we are taking from the economizer outlet. So O2 by 21 minus O2 give the excess air. Actual air. Now we need the mass of actual air. So 1 plus excess air by 100 into theoretical air, nothing but excess air. So there is a calculation of the dry flue gas also. This formula is lengthy, but if you supposed to minimize that, you just add plus one for with the excess air. Actual air, suppose you are getting 12 kg, you can add plus one because it is not more than the 1 kg dry flue gas loss. So 13 kg is the dry flue gas loss. So these are the different type of losses as per the formula it is designed. Here percentage heat loss to dry flue gas, heat loss due to formation of water from H2 in fuel, loss due to moisture in fuel moisture, moisture in air, heat loss due to particle of C to CO. So it is not coming. Fourth to fifth point is not coming. As per the BE and India Department of Power, Minister of Power, we are considered this also. Sixth one is the radiation loss and heat loss due to unburnt fly ash, heat loss due to bed ash. So finally, heat loss due to unburnt carbon. Actually, it is the main important point to play a vital role to for the boiler efficiency. This is the one. So boiler efficiency come after separating all the things, it will come the boiler efficiency. So you just see these the boiler efficiency calculation. This is my personal my company calculation. This is the design fuel for approximate analysis, ultimate analysis. This is the parameter which supposed to need for calculating the boiler efficiency. So these the design losses. The design efficiency is our design efficiency from OEM. They have given 86%, but it will come 79 80% only. So after boiler, there is one of the most important topic is compressed air system. By this compressed air system, the pneumatic valves and all valves or damper arrangement will operate on the pneumatic air, compressed air system. Earlier days, our olden days, so our people are using a hydraulic system, but hydraulic system is very costly and there is so much of maintenance and there is a leakage of oil also. For that purpose, after a lot of study, this picture has came. Compressed air system. We have a instrumentation air compressors that gives more than 6 kg. We are getting 6 kg for operating the valves is sufficient. If suppose that instrument compressor has happened, some problem has happened, it has come down to 4.5. More less than 4.5, our unit is going to trip because of the not operation of the dampers and valves. So this is a very important factor. You should concentration on that because if suddenly boiler tripping has happened, there is a lot of coal dumping has happened inside the boiler. What happened? There is a CO formation. There is separate arrangements are there, but compared to this, we should cautious for the getting the pressure. So 10 to 30% only energy reach our engine, but 70 to 90% converted into unusable heat energy. Why? Because there is a losses in air system. You just see in any plant, you are getting the losses from the compressed air system only. air system. Now, that means that instrumentation area or service area, you are getting the losses. So we should optimize these losses. And that performance, while explaining the performance point of view, I'll explain all the things. Compressor classification, there is a two type of compressors, positive and dynamic compressors. So this is the energy conservation. So axial flow compressor suited for high compression ratios, more efficient for radial compressor. So radial type reciprocating compressors use 50 to 150 CFM. Horizontal type reciprocating compressor using 200 to 500 CFM. So this is the energy point of view. For every 4 degrees inlet air results. Suppose if the 4 degrees inlet air is less than the normal value, you will get the less energy consumption. Why? Because there is a difference will come from loading and unloading. This is also one of the most energy conservation point of view. Every 250 mm of water column pressure drop increase, suction and power increases to 2%. So there is a inadequate cooling also plays a vital role. A low volume flow when 40% load compared to if the load is more less than 40%, it is advisable to go to for the vane control, not for the speed control. Why? Because speed control will take the more power than this. So the major opportunities to save in this prevention is leaks, as I explained. So this is the leakage calculation. T by T plus small d into 100. T is a time of load and unload. If you say if you have not the time provision, you just take the pressure also, loading pressure and unloading pressure also. So this is the practical problem. So due to lack of time constraints, while sharing this PPT, just go through that. So these are the end results: discharge flow, motor power, compressor power. Finally, we are getting loss of the power, 125 kilowatt like that. So while going through that, you could be able to know. So second system is fans and blowers. As we have a three type of fan arrangements. Both are the all fans are. You just see the difference. Radial fans used for industrial up to 1400 mm of static pressure, radial fan, forward curved blanks. We are all using the backward inclined fans only. Why? Because forward curved blanks need for the clean environment and high flow work, but this much of flow work we are not using now. So we are using backward curved fans. Axial flow fans meant for the PF, polarized will already I have explained. So much of air quantity needed for that. So backward curve plants gives high pressure, high flow, and high efficiency with reduced power. So these the fan affinity laws, as you know, Q1 by Q2 flow proportional to speed. Suppose say static pressure. Want to get the pressure, if you increase the fan double square, we will get the static pressure. And these the power and speed relation. If you increase the fan speed 3 times, that means speed increases. The power will get it from here. So there is a margin of the fans. Why? Because they have given the as per the design, but as per any incident happen, we need the margin of the fans. So ID fan meant for the 20% of the volume and 30% head, as the FD and the PF fan having less margin. Why? Because ID fan having more dangerous than this. If you not subtract extract the flue gas, what happen? Boiler is going to collapse and there is a huge loss from man and machinery also. So both FD and PF fans arrangement safety margins are there. ID fan requires minimum 100 mm water column to push the gases. As ID fan extract the pressure gas from the furnace, it will send those gases to the stack. After that stack, it will go to the atmosphere. So this is the velocity of air calculation. This is the formula for that. This is the mechanical efficiency calculation. Volume into delta P by 1 or 2 into power input. These are most important thing to calculate the fan performance. So density of gas, as we know. So comes under this. This is the screenshot for our plant. Primary and secondary cold and hot air arrangements. So these the both are the SF fans and PA fans. Just see. Already I have explained while showing the boiler picture. 38 degrees 44. After that, it will get the heat for 218, and this is 185. This is the pressure for 1350. So these are the separate and reheater arrangements. The cold flow coming like this, and there is a PA fan supply to the this also for hot PA. Why we are giving this is when any moisture is present, that will be going freely into the boiler. Otherwise, it will stuck the shoots. So this is the energy saving opportunity for fan and blower system. Fan mechanical efficiency, I already explained this one efficiency. Energy saving, change of impeller. Main because the flow we are getting is from the impeller only. So change of impeller with high efficiency, fan with high efficiency fan. There is a impeller material also, metallic or glass reinforced plastic using in olden days. Now they all are converted into FRP impeller only. But FRP impeller will look very cautious for high temperature and all the things, because there is a chance for damaging of the FRP. Fan speed reduction by pulley diameter modification. VFDs also plays a vital role for reducing the power consumption. Minimize the system resistance and the pressure by duct system. So this is the problem. As I explained the formula and all the things, this is the example for problem. Just go through that while sharing the presentation. So this is the result of the from the this one. So they have given 79% design efficiency. We are getting 44 due to some problems. Some leakages are there, below leakage and all the things. We have after that we are going to segregate now. So these the fans over. Next, coming to the another thing is pumps. Pumps plays a vital role to supply the water to the supply the water to the system. So there is a two type of pumps: positive and negative displacement. Positive displacement pumps are more efficient than centrifugal pump, but centrifugal pumps we are using because why? Because we need more flow. So that's why we are using centrifugal. This is the pump power formula. Q into delta H by H into density by S into G by 1000. There is a two type of this thing. How to calculate the pump shaft power, motor power, and all the things. So as per fan loss also, as per fan loss, pump having already loss. There is a affinity loss. Q proportional to the flow proportional to speed, head proportional to n square, speed square, power cube of the speed. So these are the energy conservation opportunities. Adequate NPSH head pass to suction head. Head pass to suction head is the most important to design the fan, design the pump. Sorry, pump. Why? Because if NPSH availability is not more than the design, what happened? There is a cavitation happened in the system. So there is a bubble formation and damage the metals. So stop running of multiple pumps for using. Sometimes while reducing the load, people are using both pumps. So it should be rectified. Use booster pumps. Maintenance of. So maintain less output temperature of the cooling tower for getting the coolingness of the pump. What is our supply arrangement for getting for giving the coolingness? Avoid cooling water circulation in the DC sets. DC sets designed for the air cooling is sufficient than design. But earlier our DC sets are designed for the feed water system only. So you just see the screenshot. This is the pump arrangement. The outlet already I have explained. And after dereator, there is a boiler feed pump. It will supply water to the drum through the heaters, HPO heater 1 and HPO heater 2. This is the feed control station and economizer. You just see, already I have explained. In LB heater, we are getting 10 to 20 degrees temperature, delta T. Temperature difference. You just see, this is the 184. Here we are getting 225. That means more than 40 degrees temperature is there. While coming into the here, this is the 240, 250. So HP heater 1 is most better perform than the HP heater 2. After that, it will go to the economizer. The same temperature 244. It will increase the temperature through economizer is 295. So this is the pump problem. We are getting 72%. So it is we are getting good efficiency. Designer they have given 75% only. So there is another system is cooling tower system. This cooling tower system is for the cooling purpose of the water. Generally, this water we are giving supply to the condenser. The condenser performance already directly depends on the cooling tower system only. So there is a three terminologies: wet bulb, dry bulb, and relative humidity. They just see velocity of water is less than conventional. This can reduce by drift losses 0.01%. That means velocity also plays a vital role. So air at a higher wet bulb temperature capable of pick up more heat. So each kg of air enter 21.1 degree wet bulb temperature contain 18.8 calories, leaving 32.2. As per design, they have given 10 degrees difference for inlet and outlet of the water. If we are not supposed to get that temperature, we are not getting the vacuum. While coming to the turbine part, I will explain clearly this one, vacuum and all the things. So this is the cooling water system problem. How to evaluate the performance of the cooling water system? There is a range, approach, CT effectiveness, operation loss, COC, cycle of concentration, blowdown loss. Just go through that. So these are these are practical problem. COC should come less than 2 only. If it is more than 2, you should concentration on the water chemistry, and moreover the algae formation of the cooling tower. You should cautious. So efficiency operation of the system I have given here. Water treatment should be maintained. Maintenance of the cooling tower fan by removing the all algae, and maintenance of the fins also. So these are the energy saving opportunities in CT system. Automate CT fan blade angle. Replace spray nozzle with no one. Nozzle with new one, not no one. Sorry, this is the new one. Fan balancing, maintaining correct fan tips. Maintain a COC. Restrict some flows, large flows. Maintaining cooling water temperature. Consider FRP blades. Improve cooling water pump efficiency and optimize cooling water flow rate. These are all related to energy saving opportunities. This you are not getting the any books. You just go be cautious for this energy saving opportunities. So this is the heat exchanger. Another thing is another part is heat exchanger. Why heat exchanger concept is more important? Because every our accessories like economizer, superheater, evaporator, and the HP heaters all are depend on the this heat exchanger concept. As we know, we have a three type of flows: parallel flow, counter flow, and cross flow. Now in our plants we are using counter flow arrangement only. LMTD, based on the LMTD, those performance on the depend on. So this is the air preheater. As you know, air preheater, there is a recuperator air preheater. That means one side we are supplying one side. So flue gas is going through the atmosphere through the APH. There is a basket arrangement. Once it goes to that basket is going to getting heat picked up, and while rotating this one, some place it is coming. Sorry, this is the flue gas arrangement. These are sometimes some part it is primary fan and another part is secondary fan. While rotating this one, the P and SA getting the temperature of the temperature from the basket that will go to the furnace. So these are the effectiveness of the APH and air side. You just see that. So these are the my practical problem. What is the effectiveness we are getting, and how much heat rate is going to transfer? So we are having good heat transfer rate. So another thing is reheater. Reheater already I have explained. Not this. Just see the boiler point of view here. Not this. Reheater, there is no separate sketch arrangement. These for the reheater. These also work on the LMTD only. So this is the economizer. Economizer, you know that increase the feed water temperature. While going through that, it pick up the heat from the flue gas, and it going to the water temperature is going to increase, and it will directly supply to the boiler. So increase the boiler efficiency 2 to 4%, reduce the fuel consumption, and prevents the corrosion loss. There is another accessory is superheater. Superheater, we have a three type of superheaters arrangements. One is patent, secondary, and final superheater. Final superheater is the OEM final superheater fuel gas going through the second pass, while primary and secondary went for the first pass only. So the radiant type of superheater we are using, and the superheater temperature while operating the superheater, we should more cautious. Why? Because this temperature at the superheater is more than the other devices. We are getting 540 degrees at the end of the superheater, and the OEM also supply 540 to the turbine. Less than is more difficult to give the turbine, and more than it will damage the tubes, because these are the allied tubes already having T91 and T92. So there is a separate arrangement for the attemperation. Here, if you having the more temperature, we are getting the more temperature, because combustion we can't control. Once combustion has happened, the steam temperature going to increase. So there is a two type of attemperament stages. We could reduce the steam temperature to the designed limit. So this is the main part turbine, as I have explained. This is the HP turbine. We just see. This is the HP turbine. HP turbine. So these are the stages. This is the IP turbine. These are the stages. This is the LP turbine. You just see. Already I have explained. LP turbine blades are more than the other because of the handle the wet steam. So three type of turbines already I explained. This performance we could say in terms of heat rate. So I'm going little most faster because of the time limitation. So much of these there. So this is the formula for calculating the heat rate: mass of steam into enthalpy of steam minus enthalpy of feed water plus mass of heat reheat steam, enthalpy of heat reheat HRH, and enthalpy of CRH by generation. Just go through that. Yeah, this depends on these are the main factors which heat rate depends. Low temperature, steam, and pressure. Already I have explained this point while you were explaining the boiler. Poor vacuum, high cooling water difference, and insufficient cooling flow. So this is the screenshot for the turbine in our plant. Just see, go through that once. This is the CRH and this is the HRH steam. This is the LP turbine. This is the LP heater one. Already I have told you. So this is the HP heater performance. HP heater, as you know, TTD. There is a two terminologies. One is TTD and another one DC approach. Based on these two terminologies, that heater performance is going to calculate. So bleed arrangement, bleed steam is coming from the turbine for heated up the feed water or condensate water. So this is the result. So we are getting to TTD. This should be less than 4. If the TTD is more than 4 degrees, what happens? There is a initially we could say that there is a fouling happened in the tubes of the heater. So this is the condenser. Already I have explained. The exhaust steam is coming at one end and condensate water is going to the other end. This is the special arrangement. We have a condenser, around 14,000 tubes are there. Chromium aluminum tubes for supplying feed water to the condenser. This feed water coming from the pumps from the cooling tower. Cooling tower, this inlet is coming from the cooling tower. Outlet is also going to the cooling tower to cool the water for the sake of the water convenience. So this is the condenser condenser performance. So this is the condenser arrangement. So cooling water inlet and outlet. So this is the formula for the exact problem for the condenser. This is the design point of view. This is my calculation point of view. We are getting more than that, but they have meant for the two pumps. Now we are using only one pump only. So these are at the end of the things, energy audit details. As I explained earlier, this is the practical energy audit. Brief summary I have shown here. There is a two type of investment: small investment, medium investment, large investment. Just go through that. Less than 1 year, 16 recommendations are there. I was also one of the part of this energy audit. Annual saving we are getting 874. These are all the lakhs. For cost of implementation is less. So what is the payback period? 0.16. To 12, we just see that months of will come. This is the medium investment, and this is the large investment. That means it will the large investment need more time to get the investment back. So these are as 1323.73 lakhs for the saving potential includes this include coal cost also, and 15.32% against the total annual bills. So cost of implementation is this much. So these are the brief short-term savings. Just go through that. Yeah, for electrical system, bus voltage coordination, switch off unloaded transformer. So while less load and transformer by observing the transformer loading, we'll switch off the one transformer, and that transformer load will go to the another transformer, that parallel transformer. Reduce generation loss by PF improvement. PF improvement comes from the capacity bank increase of the size. We have a capacity bank. We will get it 0.96, but it will come to 0.99 by increasing the battery system. Electrical drives. So forced ventilation fans. As this is also one of the good recommendations they have given. Forced ventilation fan working on the density difference. No need for the power supply. So they have given the recommendation, and avoid damper control. These are the operation point of view. Avoid air leaks, as I explained while explaining the SFN concept. Should avoid the air leaks. Otherwise, fan performance also going down. This also I have explained. Outline the main steam and reheat steam parameters close to the design. That means present temperature we should supposed to give correct values. Next, pumping system. So we have earlier we have operated two pumps. Now we have operated one pump only. Replacement of CT makeup pumps and PSF fans. These are all the recommendations. So these are, as earlier I explained, these are the same thing I have given here. Energy conservation, avoid damper control, reduce turbine heat rate, same thing. So finally, thank you, and moreover, I'll show you the energy audit report. One moment, please. Yes, this is the energy audit report they have given, as I have shown you clearly. For each and every system, we have considered and we have make the statement. So these are the investments, as slides I have shown this. 3 people has came that time.
Dr. Naveen?
Yeah.
Yes, actually, these are not visible, these reports.
Not visible, right? Okay. That's it. My presentation is that's it. If any question, you just ask me and I can explain.
So now I would like to invite Professor T. Srinivas to deliver a vote of thanks to Dr. Naveen Kumar ji.
Okay. Thank you, Dr. Rajan Kumar. First, let me thanks Dr.
Sorry, sir.
Kumar.
Actually, I have not seen camera in off condition.
No. It's fine. I'm able to see you. First, thank you for accepting our invitation and delivering these elaborate lectures, especially on thermal power plants and auditing. And also, I think for we and participants will the very detailed power plant, each and every component, superheaters, evaporator, economizer, especially boilers, and that very detailed. You gave very detailed explanation, and that's more useful to even some scholars also here in the thermal field and mechanical engineering. I hope they got enough. Industrial information, I can say, because you shared your expertise, especially in the energy auditing. You are the certified auditor, so that energy auditing and the information about the practical information about these power plants and its component is more useful to our things, because it's a poly generation. Power generation is a main outcome. That's main product. First product, I can say. First product is a power generation. The rest of the outputs like process heat and others is a secondary only. So the primary output, which is a power generation, you covered very well, including that means identification of these losses. That's bottlenecks in the form of auditing, checking and auditing. It's a nice presentation, and thank you once again. Yeah.
Yes, sir. Shall I leave, sir?
We'll continue the next section.
Okay. Thank you, sir. Thank you.
Thank you, Dr. Naveen.
Yes, sir. Thank you, sir.